The goal of this presentation is to introduce DHXPOT, which is a sensitivity analysis tool on district heating potentials and costs. DHXPOT can be used for identification of the district heating potential in large-scale areas. It identifies suitable areas for implementing a district heating systems and shows us the size and extent of the potential district heating area. It provides indicators on average and total heat demand in the potential district heating areas as well as the district heating potential. It is possible to study the impact of evolving market share and heat demand on a district heating area. And also, it's possible to have a look into the district heating distribution grid as well as service pipe cost. And the tool provides some approximation of the trench length. Using DHXPOT within the EnerMaps data management tool has several advantages. There is no need to have knowledge of programming nor GIS, and you can start using the tool by giving data. You can get new metrics out of existing data and use own or default country-specific construction cost to estimate the overall cost of pipelines. The tool is suitable for calculation on a larger scale areas like NUTS 3 or even higher. To fulfill the expectations from the tool, certain assumptions should be made. For example, market share and heat demand evolves uniformly in all areas. Additionally, calculation is done from socioeconomic perspective, therefore the location of the existing grids are not considered. From the end of the investment period till the end of the depreciation time, the market share and covered demand remains the same. We consider a 30 mm pipe diameter for the service pipes. Even though market share gradually changes, we consider pipes covering highest demand in the investment period. And for the calculations, we consider the base year of 2015. In order to find the district heating potential areas, two conditions should be satisfied. First of all, the levelized cost of heat for the distribution grid should be below a given cost ceiling. Secondly, the heat demand within a potential district heating area should be higher than a given minimum heat demand for the district heating areas. Once these two conditions are satisfied, then we get the potential district heating areas. For the calculation of levelized cost of heat for the distribution grid, we have the following formulation, where we have the Q as the heat delivered in each year, C1 and C2 are the construction cost coefficients and constants, dA is the average pipe diameter, and W is the effective width of the district heating system, district heating distribution pipes, which relates to the relation between area of the land and length of the pipes. This is similar to the standard levelized cost of energy formulation, where we have the sum of the cost over the lifetime divided by sum of energy produced over the time. For each member state, DHXPOT uses cost coefficients related for that member state. This can of course be adjusted by the end users as well. On top of that, for the effective width within the very low plot ratio areas, we have defined a new formulation where market share comes into play and has impact on the effective width and therefore on the levelized cost of distribution grid. Now that we got some ideas of what is happening in the background, let me show you what the user should expect in the interface of the tool. There are two sets of the input parameters: default inputs and user inputs. As default, for each member state, a construction cost coefficient is given. This can, however, be changed by the user and provided by him or her. Additionally, as a default raster, layers, heat demand density, and gross flow area density maps are given, which will be used for identification of potential district heating areas. The user, on the other hand, can provide the following parameters: market share in person for the start and target years, expected accumulated heat saving in the target year, referring to the amount of heat that can be saved as a result of retrofitting, for example, investment period in which market share increases or decreases, depreciation time, interest rate, grid cost ceiling in district heating areas, which is a parameter showing that distribution grid cost should not exceed this value. And finally, construction cost coefficient, which is an optional parameter and is already provided by the tool itself. As output, on the other hand, we have three sets of outputs: indicators, layers, and figures. As indicators, the user can expect total and average demand in the selected region and in the potential district heating areas within that region, the size and extent of the potential district heating area, maximum potential of district heating system through the investment period, energetic specific district heating distribution and service pipe cost, a specific district heating distribution grid cost per meter, total distribution grid cost, and total distribution grid trench length. As layer, a shapefile is provided and can be downloaded to identify the potential district heating areas. And additionally, for sensitivity analysis, we will provide some figures. In this slide, I brought up the case study of Austria, where I have calculated district heating potentials under different connection rates or market shares in the start and end year, as well as the grid cost ceiling. One clear output is that the district heating potential increases as we increase either the grid cost ceiling or the connection rate, whether in the start year or in the end year. However, it is worth mentioning that the highest influence can be seen by the market share. In other words, increase of the market share has the higher impact compared to increase of the grid cost ceiling. I have also looked into the cumulative district heating potentials in this graph. So here on x-axis you see the coherent areas or potential district heating areas, and in the y-axis you see the cumulative district heating potential. It can be seen that most of the potential district heating areas are pretty smaller areas, and only a few larger district heating potential areas can be spotted, which are related to the larger cities in Austria. Another aspect that I looked at was the comparison of grid costs in district heating areas and also district heating potential in those areas. So here again in the x-axis you see different coherent areas or potential district heating areas, and then on the primary axis you see the grid cost in euro per megawatt hour in each of those potential district heating areas, and in the secondary axis you see the potential. So we see that the very low grid costs are related to areas with not very high potential. So there is no exact correlation between the dislocating potential and grid cost in that area. We see that here in a larger areas or areas with higher potentials, we have relatively higher grid costs compared to those smaller areas. But generally, we see that for certain smaller areas, we are reaching to our cost threshold of 50 euro per megawatt hour, as it was related to one of our scenarios. The same comparison I made between grid cost and heat density in the coherent areas. And we see that in areas with very low grid cost, we have pretty high density. So heat density can be considered as a important factor for decreasing the overall grid cost or average grid cost ceiling. I hope I could have given you some ideas of DHXPOT, which will be part of the EnerMaps data management tool. EnerMaps project has two outputs. One, research community gateway, where you can look into the data sets and different projects, outputs of the project and research works, and the data management tool, which is used for the visualization and manipulation of data. So DHXPOT will be part of the data management tool and will be soon available on the platform. I thank you very much for your attention, and I hope you have enjoyed this presentation.